right? Yeah, let me share the screen.
Yes, sure, Kenta.
So can you now see my screen? Let me make it bigger.
If you can, yes, it would be nice if you can.
So do you now see my screen with full screen?
Yes, yes,
Yeah.
we see
Okay.
it.
Great.
If then it will not be too small, even this is fine.
Yeah, okay, good.
Okay, so we immediately proceed to the second talk today. And the second talk is by Kenta Osuga from University of Sheffield. And Kenta will tell us about N=1 super topological recursion. Yes, please.
Okay, so first of all, I'd like to thank the organizers for this invitation. It's my great pleasure. Oh, let me actually time myself. It's my great pleasure to speak here. But before talking about the super topological recursion, in case some of the participants were not at Andrea's talk, let me give you a nice advertisement. So at the University of Sheffield, we are organizing an online conference about BPS states, mirror symmetry, and exactly WKB. So if you're interested, please go to our website and please register before the 18th of June. All right, so first I'm going to tell you the story of the topological recursion. And in my view, the topological recursion started with a fundamental structure called abstract loop equations. And because they are equations, you can try to solve these equations, in particular by utilizing the data, like geometric data of a spectral curve, and by picking residues at some ramification points. And this computational technique is none other than the topological recursion. And a few years ago, Kunsavich and Sobelman proposed another approach to solve topological recursion or abstract loop equations. And basically, you transform the abstract loop equations into the language of differential constraints, or in this talk, more specifically, Virasoro constraints. And this approach is now known as airy structures. And throughout my talk, I would like to introduce the supersymmetric generalization of both of them. So I want to construct the super structures and super topological recursion. And of course, I have only half an hour, so I have to skip many details, but hopefully at the end of the talk, you will grasp an overview of this development. Okay, so let me first start with super airy structures because it's easier. So Gaetan gave introduction about airy structures on Wednesday, so it's yesterday. And to highlight the difference for us, for super airy structures, the fundamental, the vector space underlying is Z2 graded, namely bosonic or fermionic. And V0 is a bosonic vector space. And I would highlight all fermionic dependence with red colors so that you can visually see which ones are bosonic and which ones are fermionic. And now the fermionic vector space is the V1 plus additional bit. And you will see why I have this additional fermionic vector space shortly. And as Gaetan did, we now introduce coordinates for each vector space. So X is a bosonic variables on V0 and theta Grassmann variables for V1. And theta 0 is for this extra fermionic vector space. And then we introduce grading in a natural way, namely for all bosonic and fermionic variables, we assign degree 1, and then introduce formal parameter h bar, whose degree is 2. Then now the space of differential operators is spanned by these generators. So x is an h bar d by dx, and h bar they are exactly the same for airy structures. And you naturally extend with fermionic variables. Okay, so far everything is just natural. You just impose some Z2 grading with Grassmann variables, and that's it. And here is a definition of a superstructure. A superstructure is a set of parity preserving operators, so either fermionic or bosonic, but there's no mixture, satisfying the following conditions. One, for bosonic labeling, the bosonic differential operator starts with h bar dxi, this is degree 1 term, plus higher degrees. So this is exactly the same requirement for the standard airy structure. Now for fermionic labeling, we basically impose the same thing. So for fermionic differential operators, the degree 1 term starts with this d by d theta I plus higher degree. Okay, so it's natural. And then depending on the parity of differential operators, either commutator or anti-commutator should satisfy some compatibility conditions that I'm going to skip the details. Okay, but you see, so far it looks quite natural. You just impose Z2 grading, that's it. But now I'm going to tell you an important remark. So in the definition of superstructure, we do not require the presence of fermionic differential operator with this theta 0 in the degree 1 term. But this theta 0 does appear in degree 2 terms here. So intuitively, you can say that the number of variables you have, this x, theta, and theta 0, is number of differential operators, these, plus 1, because we are missing these differentials. And because of this reason, we call this theta 0 the extra variable. And this is a technical difference, but crucial difference from the standard Airy structures. Okay, but if you accept this fact, everything else actually works as expected. In particular, the reason why Airy structures are interesting is not because of the definition itself, but more like because they exist and unique associated free energies. And that works with the superstructure as well. So more precisely, given a superstructure, there exists a unique power series, which we sometimes call free energy, of X bosonic variables and Grassmann variables theta i's, and with this extra variable as well, such that free energy must be bosonic, and free energy does not have terms of degree 2 or less. This is the same condition for the standard Airy structures. And then this e to the f, sometimes we call the partition function of the Airy structure, is annihilated by all the differential operators you have in your super Airy structure. And then if you wish, you can expand this free energy with these in this way. So the condition 1 says that we have to have even number of fermions here. So you have 2m fermions. And the condition 2 says that the sum should start with this combination. And then the condition 3 gives us a set of recursive equations for these coefficients fgn/2m. And throughout my talk, I would use this notation. So the first integer tells you the genus, and the second one is the number of bosons, and the third one on the right-hand side of the slash gives the number of fermions. Okay, so this is basically a definition and theorem for superstructures. And then now we move on to vertex operator algebra. So as we learned from Gaetan's lecture, many interesting examples of Airy structures are coming from vertex operator algebra. So then you may ask, can we find any interesting examples of super Airy structures from vertex operator superalgebra? And here is the answer. So this slide has many informations, but you can forget about the details, and I have only 2 comments for you. First, this collection of differential operators, J, gamma, L, and G, and they are differential operators by these definitions. And they generate an extension of the n=1 super-Virasoro algebra. Okay, so this is indeed what we are interested in. So this is a nice algebra. And the second remark is that, excuse me, the second remark is that these differential operators do not define superstructure yet. So we need extra step to make this set of differential operators into a superstructure. And here is the way to make it superstructure. So now you fix 3 parameters, tau, phi, and psi, with some of these technical conditions that you can forget. And now let's think about the differential operators phi. Okay, so then what you have to do is you take a conjugate of J, gamma, L, G in the previous slides by this big phi. And now I name H1, H2, F1, F2 for these differential operators. And now because you have chosen tau, phi, and psi, these H's and F's are sensible to the choice of tau, phi, and psi. And if you know the story of Airy structures, only psi is kind of new data for you. All right, so then the proposition is that for any choice of tau, phi, and psi, satisfying these technical conditions, these differential operators defines the superstructures. So, okay, in some slides ago, I showed the definition of superstructures, and they actually satisfy those definitions. And because of the theorem of the superstructure, there exists a unique free energy or power series associated to this choice of tau, phi, and psi. All right, so this is the punchline of this section. It's very important. So you can think of, if you don't know the detail about area structures or superstructures, you can think of it as a machine that takes the choice of tau, phi, and psi as the initial data, and then it spits out FGN/2m coefficients of the free energy. Okay, so this is the punchline from this section. And then underlying algebra of this machine is none other than the n=1 super Virasoro algebra. Okay, so now we move on to the geometric counterpart, super topological recursion. So this is the definition of a local super spectral curve. It's very important that we have local, and we do not have a good understanding of global super spectral curve, but this at least works for in this context. So local super spectral curve starts with, now it's not just a disk, but you actually have to think about a disk of a super manifold, so 1/1, and you have bosonic variable Z and Grassmann variable theta. And then the three of them are actually kind of the standard definition for even a local spectral curve. Namely, you have involution swapping the sign of Z, but leaving theta invariant. And now a choice of tau L, which is encoded in this one form. But again, I'm using the same notation, so genus 0, 1 boson, and no fermions. And tau is given with this expansion parameter. And now a choice of phi is encoded in the holomorphic part of omega 0(2/0). So it's bosonic 2-point functions. And then to make it a super spectral curve, you need additional data, which is basically a choice of psi encoded in this antisymmetric differential. So you have genus 0, no boson, but 2 fermions. So it has to be antisymmetric. And let me, okay, so I'm pretty sure for many of you, this is a new object. So let me justify what this is. Okay, sorry, but before that, this local super spectral curve has only 3 parameters that you can choose: a choice of tau, and phi, and psi. And if you choose 3 of these parameters, you completely fixes a local super spectral curve. And now a justification. So this funny big theta here, if you take a square of it, you get Z dz. So you can think of this big theta as a fermionic version of a square root of Z dz. And you can think of this kind of dual description of superconformal structure with Ramon puncture at the origin. This is a Ramon puncture. But okay, keep this in mind. If you take the limit such that Z1, Z2 are close to each other, and this antisymmetric differential that we newly define behaves like this. So it has a simple pole on a diagonal, and it's a half-order differential, but it's fermionic, but it's half-order differential. So this is exactly the expected form from conformorphy theory perspective. Okay, so and then given a local superspectral curve, we presented a set of recursive formulae that computes multilinear differentials. Now you have n bosonic variables. They're symmetric under the permutation of these, and antisymmetric fermionic variables. And we call this set of recursive formulae the n=1 super topological recursion. Okay, and then of course, now I don't have time and space to present all of the formulae, but let me tell you one of them. So suppose you want to compute this differentials, and then this is the recursive formula that you have to use to compute this guy. And I think for first 2 lines, many of you are familiar with. It's basically extension of the standard topological recursion. You are gluing 2 bosons, and here you are again gluing 2 bosons. Okay, and then spits out this one. And the red highlighted lines are probably new to you. Now, okay, remember that variables on the right-hand side are fermionic variables. So now you glue 2 fermions, and this one again, you also glue 2 fermions for the contributions to this computation. Okay, so it's like you're kind of doing pair-pans decomposition, but now you have contributions from fermions. Okay, so and then okay, anyway, so this is the definition to recursively compute this guy. And if you want to compute differential for the fermionic variable, you have to use a different recursive formula, but we actually gave that in our paper. Good.
What does dz get though?
Sorry, what?
What is dz?
Dz, oh, it's a derivative on this z. So you actually have to take a derivative on these differentials, but whenever it appears, like z appears, so that even if after you specialize, it's not going to be 0.
Okay, thanks.
It's kind of similar to the Q form.
And how in fermionic case z is related to sigma of z?
Kz.
No, k, z, the variable z and sigma of z.
Or sigma of z here, because I'm doing the local special curve, it's just minus z.
It's the same. So I mean that, yes, so it doesn't mean, it doesn't distinguish where we are in fermionic part or bosonic, right?
Yeah, so this one, so the z appears on the fermionic side.
Mm-hmm.
Is that clear?
Okay, yeah.
Yeah, okay, yeah. All right, so, sorry, so the summary of this super topological recursion is that, so the important remark from this formula is even though it might look a little complicated, there's no degrees of freedom. So it's a universal recursive formula. And if you choose a choice of special, if you choose a local special curve, and it just generates everything recursively. So you can think of this super topological recursion as a machine that takes tau phi psi as the initial data, and the outputs are multilinear differentials, omega gn / 2n. Then if you remember from super Airy structures, that is another machine that does basically the same job, but outputs are now coefficients of the free energy. And then, of course, you may ask, are there any relations between the coefficient of free energy of the super Airy structures or the differentials of super topological recursion? And here is a dictionary between the super Airy structures and super topological recursion. So given a choice of tau, phi, and psi, you can indeed find a natural basis of expansion, dxc and eta. I think you are familiar with this dxc basis, but eta is a basis for fermions. And if you expand this differential with this basis, and the coefficients are exactly the ones you would get from the corresponding super Airy structures. Okay, so this is the dictionary between the super topological recursion that I presented a few slides ago and the super Airy structures. Okay, so now in the last, okay, so I think I want to leave 5 minutes for questions. So I think I'm doing good in time. So in the last part, I would like to tell you what kind of applications we can think of from this supersymmetric topological recursion. I think you are more interested in these directions. But before doing so, let me compare the super topological recursion with the standard topological recursion. And from a local perspective, topological recursion is a machine that takes a choice of omega 01 or equivalently choice of tau, and choice of omega 02 or equivalently choice of phi, and it generates omega gn from the multilinear differential of the topological recursion. And of course, super topological, it does the same job with extra fermionic data, and you have fermionic variables as well. Now, then you may ask, are there any relations? If you take the same tau and phi, are there any relations between the differential from the topological recursion and differential from the super topological recursion without any fermionic variables? And here is the answer. For any choice of tau, phi, and psi, you can easily show, this is actually a trivial result from the recursive formula, that at the genus 0 level, they're exactly the same. But for higher genus, you get fermionic contribution. Basically, you get a genus coming from a fermionic loop so that they are not going to be the same anymore. Okay, but there exists an interesting choice of the initial condition. Namely, if you set both phi and psi to 0, but leave tau arbitrarily, then for all genus G, you can show that the differential from the super topological recursion is related to the differential from just the standard topological recursion by just the power of 2 to the G. And you might find this somewhat similar to what Danilo showed on Tuesday. And also, if you remember from Paul's lecture on Monday, he said that, okay, even though he started with moduli space of super-Riemann surfaces, the properties can be captured by standard moduli space of Riemann surfaces. And I think, I don't have any proof, but I think this is it's describing basically the same thing from different perspectives. But anyway, it's just a comment. But if you run the super topological recursion, you of course get non-zero this differential with fermionic variables too. Okay, so keep these two formulae in mind. And now let's think about applications. For the simplest case, let's choose tau3 to be non-zero, but anything else is zero so that we can use these formulae. And then from physics, we actually have the answer. The super topological recursion computes correlation functions of minimal model coupled to Liouville's supergravity. And this is indeed something what we expect from physics. Now let's think from enumerated geometric point of view. Then an interesting question arises. So in this data, we know that if we run the topological recursion, it computes conservative Witten intersection numbers. And because of this formula, these one also computes basically the same thing, just up to the power 2 to the g. Then you may ask, are there any interpretation for this non-zero differentials with fermions? And this is an open question, and I don't have the answer, unfortunately, but I'm very happy if anyone has ideas to discuss. And now you can think another application, namely, again, you choose phi and psi to 0 so that we can use these formulae, but choose tau from the expansion of cosine. And what we learned from Stanford Witten and also Paul's lecture on Monday is that this omega gn from the topological recursion computes volumes of modular space of super-Riemann surfaces. And this formula shows that, okay, this guy does the same job. And then again, you ask the same question. Can we find any enumerative interpretation for non-zero differential with two fermions? And again, this is an open question. I wish I could give you an answer, but yeah. All right, so another application I'd like to connect to what Gaetan said yesterday. So very roughly speaking, Barad, Bouchard, Stambra, and Kreutig showed a mutual relations between topological recursion without branch covers and Guyotto vectors in conformal blocks and Nekrasov-Quantum function for n equal to gauge theory. But more precisely, they basically connected more like here. Then the because of the AGT correspondence, the Guyotto vector can compute the Nekrasov-Quantum function. But then you may ask the same question, okay, can we extend their work with supersymmetry? And the answer is yes. Oh, sorry. And okay, I don't have time to talk the detail, but you can indeed construct super topological recursion without branch covers. And indeed, this actually has some geometric interesting properties. But anyway, so the upshot is that it can compute the Guyotto vectors in super conformal blocks instead of just the conformal blocks, as expected. And the corresponding gauge theory is U2 theory on C2 mod by Z2. So mod by Z2 basically kind of it's coming from the supersymmetric thing. Okay, so at last, I'd like to tell you another application to matrix models. So you can actually apply the super topological recursion to compute correlation functions of supersymmetric analogs of Hermitian matrix models, and they are called super eigenvalue models. And then there exist two sectors. The Nevius-Schwarz sector, it works everything fine, and it's actually very simple. It turns out there's some relation to Hermitian matrix model as well. So this is just, it works as expected, no surprise. And you might ask, okay, so far what I've said sounds like everything works as expected. Are there any surprise or are there any supersymmetric effects that we can find? And here is basically a surprise. So if you investigate super eigenvalue models in the Ramon sector, first of all, this relation does not hold anymore. Okay, so there's no direct relation to the standard recursion. So you do need the supersymmetric topological recursion. And another surprise, like this is actually probably the biggest surprise I've had so far, that okay, independently, I found the bosonic spectral curve in this form. So there are two branch points. When X is TR, it's like the regular Airy-like branch point. And when X is 0, you have Bessel-like branch point. Okay, this is just a consequence from supereigenvalue models. But then the point is, it turns out there's no contribution coming from Bessel-like point because of supersymmetric cancellations. So all you actually have to take is only the branch points at when x is clear, but not when x is 0. And I don't know why this is happening, but this is an observation, and it's very interesting. All right, so to wrap up, I think I'm doing good in time. So the main message here is that because we are doing local superspectral curve, a choice of tau, phi, and psi completely fixes a local spectral curve, local superspectral curve. Or equivalently, it completely fixes superstructure coming from vertex operator algebra. And then, as I said, superstructure or equivalently super topological recursion, they're machines that take tau, phi, and psi as the initial data, and it computes either coefficient of the free energy or the differentials. And they're equivalent to each other, as I showed in the dictionary some slides ago. And then there are many more to be investigated. And so, yeah, if you have any ideas, okay, probably the first question is most interesting for many of you. But yeah, if anyone has ideas to discuss, I'm very happy to listen to. And this is the end of my talk. Thank you so much.
Thank you. Thank you, Kent, for a very illuminating talk. And I think that we can reward you with several good questions. Please. Feel free to unmute yourself and ask questions. Well.
So I have a small question. So
yep.
In the super matrix model setting, do you have a meaning for these omega g and 2m for 2m different from 0?
Yes, from matrix model perspective, yes. So they are exactly the correlation functions of these matrix models. So from physics point of view, yes, we have interpretations. And that's even true for, it's even true for this case as well. We have an interpretation from physics, and this actually computes correlation function with fermions for the Liouville gravity. But what's missing is more like enumerative interpretation. And I don't have, at least at the moment, I don't have any clue what they are computing, but they are non-zero.
Okay. Thanks.
Okay. I have a question. Actually, it's also from my childhood.
Okay.
For n equal 1 supersymmetric series, we often have what is called a superfield formalism, which actually, you know, it mixes actually the odd and even variables in one object. Do you, because apparently when you have this exponential of the free energy, in the free energy there are only even terms, and this formalism is somehow allows to introduce these odd terms, but of course they will be even, because the price is the price is to introduce some new non-commuting variables beside your theta. Do you observe something like that? Do you have some room for this in your case? Maybe this theta naught can be interpreted as this additional variable. I don't know, it's just a vague idea.
Yeah, so I think you're asking more like, can this free energy, these coefficients can be fermionic or not? That's another way of saying?
Yes, of course, they not be completely fermionic, because anyway, they must be even at the end of the day if they are exponentiated.
Yeah, right. So yeah, it's a very good question. And yes, we do have expectation coming from matrix models. And then that basically from the super topological recursion point of view, you would introduce omega 0, 0 / 1, so fermionic one form. And then I have expectation from matrix models, but and then that would probably actually, that question actually goes to the definition of global spectral curve, because we have the bosonic algebraic curve and you can have fermionic algebraic curve. And that actually we get from matrix models. But at the moment, we don't have any mathematical definitions in that formalism. But it's definitely possible. And then I would like to investigate more about that direction.
Okay, okay,
So-
but
Can I ask a question?
Yes.
So when you say a fermionic differential form, do you mean that you have some function, which is a function of both odd and even coordinate, and some dx or dz, or do you have also d thetas?
Yeah, so I have these thetas, more like actually a combination of those. So you're probably asking about this big theta.
Yeah. So
So it's not actually d theta, but if theta, this actually behaves like it's a section of the square root of the canonical bundle.
mhm.
And then you have this guy as well. So now,
Yeah, but all your differential
Because-
form, because
because
that's a
this
vector field. Well, that's
yes.
well, yeah,
this operator has a standard structure of what is called the generator of supersymmetry transformations.
yes. But if you want to integrate forms over your supermanifold, of course, like because d theta is commuting.
Mhm.
If you write a differential form,
Anti-commuting.
no, theta is anti-commuting. D theta is commuting.
No.
Yes.
Uh,
Yes, it's like if you go back to, I don't know, Siegel's book Superspace.
Yes, DC do not.
oh, okay, I know what you mean by
To
commuting.
have
but-
anti-commuting variable, you need to introduce integral forms, which are like delta of d theta, and those are anti-commuting. It's also shown in, I don't know, Witten's super integration and super Riemann surfaces.
Yeah, the forms are commuting. I know what you mean, because basically you take a wedge of anti-commuting things so that it ends up being commutative. That's true.
Yeah.
Yeah, so if you want to generalize with those differentials, then actually, like you can think of this big theta 1 and theta 2 as you said, but the important property we wanted to have is like the square of theta has to be z dz. This is actually important for us, at least. For this formalism,
see.
this was important property, and that's why we define big theta in this way.
I see.
Yeah.
Okay.
So, okay. This formalism was born last year, so I think there are many ways to refine it in the future.
Okay.
Thank you.
Okay, so we have to move.
yeah.
And again, so really thank you, Kento. So
Thank you.
okay.